Hello dear students, hope you all are doing well. So I'm going to start a new topic in this video. So next, let us see what is Raoult's law. Before we start with Raoult's law, let us first try to understand vapor pressure. Let us take solvent, let it be water. Let's take water in a closed container. Now, when we heat at the boiling point temperature, water will be converted to vapor phase and it will occupy the space here. Now, if we keep heating, more amount of liquid will be converted to vapor phase. So, we'll reach a point where the vapor and the liquid phase of water will be in equilibrium. So, at this point, the pressure exerted by these vapor molecules on the surface of this liquid is known as vapor pressure. So according to Raoult's law, if we take a mixture of volatile liquids, so let us take liquid A and liquid B, and both are volatile in nature. So on heating, both will be converted to vapor phase. Now both A and B will exert some pressure on the surface of this liquid. So the pressure due to A is directly proportional to the mole fraction of A. That means if the mole fraction of A increases, the pressure exerted by it on the surface of the liquid will also increase. Similarly, the pressure due to gas or vapor B is directly proportional to the mole fraction of B. So according to Raoult's law, the vapor pressure of a component in a solution is directly proportional to the mole fraction of that component in the solution. So this PA is equal to, in place of proportional sign, if you use equal sign, you need a constant. So the constant is PA naught, where PA naught is the vapor pressure of solvent A. That means when it is only the solvent, when you are not considering solution, that means it's a pure solvent. This is the vapor pressure of solvent A. It is also known as partial pressure of A. Similarly, from here we can write PB is equal to PB naught XB. Let us consider a solution of two volatile liquids, A and B. So according to Raoult's law, PA is directly proportional to mole fraction of A, which implies PA is equal to PA naught XA. Let this be equation 1. Similarly, PB is directly proportional to mole fraction of B. PB is equal to PB naught XP. That is mole fraction of B. Let this be equation 2. According to Dalton's law, total pressure on the surface of the liquid P is equal to pressure due to A, that is PA, plus pressure due to B, that is PB. So from equation 1 and 2, if you substitute PA and PB, you'll get PA naught XA plus PB naught XB. Now we know mole fraction of two components. If you consider two components, the sum of the mole fraction of the two components, that is mole fraction of A and mole fraction of B, is equal to 1. So from here, we can write mole fraction of A is equal to 1 minus mole fraction of B. So if you substitute the mole fraction of A equal to 1 minus mole fraction of B, in this equation, you'll get PA naught 1 minus XB plus PB naught XB. So if you simplify and arrange it, you'll get PA naught plus mole fraction of B, PB naught minus PA naught. So from this equation, we can see the total pressure can be expressed in terms of the mole fraction of one of the components. It can be expressed in terms of the mole fraction of A, or it can also be expressed in terms of mole fraction of B. Now if you study this equation graphically, let us take vapor pressure along y-axis and mole fraction along x-axis. So we have this equation P equal to PA naught XA plus PB naught XB. Now at this point, let the mole fraction of A is equal to 1. So if the mole fraction of A is 1, the mole fraction of B will be equal to 0, because mole fraction of A plus mole fraction of B has to be 1. So if the mole fraction of A is 1 and mole fraction of B is 0, the total pressure is equal to, P will be equal to PA naught multiplied by 1, since the mole fraction of A is 1, plus PB naught multiplied by 0. So the total pressure will be equal to PA naught. So we'll get here PA naught. If we move from left to right, the mole fraction of A will decrease and the mole fraction of B will increase. So at this point, mole fraction of A will be equal to 0, mole fraction of B will be equal to 1. So if you put mole fraction of A equal to 0 and mole fraction of B equal to 1, the total pressure will be equal to PB naught. This represents an ideal solution. So if you get a curve, according to Raoult's law, if you get a curve of this nature, the solution is ideal solution. So our next topic is ideal and non-ideal solution. So according to Raoult's law, whichever solution follows Raoult's law is known as ideal solution for all concentration. So let us take a solution. And if this solution follows Raoult's law for all concentration, that means whether you increase the concentration, decrease the concentration, if it's following the Raoult's law, the solution is said to be ideal solution. And if it does not obey Raoult's law, the solution is said to be non-ideal solution. Now, non-ideal solution, they are further classified as positive deviation and negative deviation. That means the non-ideal solution, they will not obey Raoult's law. So they will deviate. So they can deviate in two different ways. Either they will deviate toward positive deviation or they will deviate toward negative deviation. So we have positive deviation and negative deviation. So let us consider a solution of A and B. Now, if we take only A, there will be AA interaction. If we take only B, there will be BB interaction. Now, if we take a solution of A and B, there will be AB interaction. Now, depending on A-B interaction weaker than AA and BB, or AB interaction stronger than AA and BB, we have these two different deviations, that is positive deviation and negative deviation. In case of positive deviation, AB interaction is weaker than AA and BB interaction. Whereas in case of negative deviation, AB interaction is stronger than AA and BB interaction. So for example, for positive deviation, you can take the example of ethanol and acetone. So if you take a solution of ethanol and acetone, it will show positive deviation. The reason is, initially when you take the ethanol solvent, that means if you take only ethanol, there will be strong intermolecular hydrogen bonding. So when we add acetone to ethanol, the ethanol will break the intermolecular hydrogen bonding between the ethanol molecule. The acetone will break the intermolecular hydrogen bonding between the ethanol molecules, which will result in AB interaction. That is, the interaction between ethanol and acetone will be weaker than the interaction which is already there in ethanol, that is intermolecular hydrogen bond. That's the reason the solution will show positive deviation. For negative deviation, you can take the example of phenol and aniline. So in case of phenol and aniline, the interaction between phenol and aniline is stronger than the interaction between phenol molecules or aniline molecules. Next topic which we are going to study is colligative property. So colligative property is a property which is dependent on quantity, irrespective of the quality. That means the colligative properties are those properties which depend only on the quantity, irrespective of the nature of the particle. Say for example, if you take a solution or a solution of two liquids or a solution of solid in liquid. So if you take a solution and if you study the properties of solution, and if the property is purely dependent on the number of the particle, that means the quantity, rather than whether the particle is big, small, whether it is gas or liquid, the property is said to be colligative property. So there are four important colligative properties which you have to study in details. They are relative lowering of vapor pressure, elevation in boiling point, depression in freezing point, and osmotic pressure. So we'll study each of these properties in details. We also have to do numerical from these topics. So we'll continue with this chapter in the next video. Thank you.